Okay, so what we have been looking at is scalar quantum field theories, scalar QFT, where one starts with a Lagrangian density, which is given by T minus V, where T has del mu phi term, and V is a potential, which is a particular power law. So this is a phi to the power n, and lambda n is the corresponding coupling. You can consider multiple values of n and consider a potential which is sum of such terms, but for the purpose of our discussion now, we will keep n fixed, but we can consider different values of n. Then we developed diagrammatic tools to study perturbative quantum field theory with this kind of a Lagrangian. These tools has the diagrammatic tool says that you can draw diagrams, topological diagrams, where by attaching certain elements which are propagator and the interaction vertices. If you have phi cube theory, then you have 3 vertex. If you have phi 4 theory, you have 4 vertex, and so on. Using these elements, you can construct various diagrams, and those diagrams will represent physical quantities, for example, Green's function. So Green's functions, we have shown the diagrammatic representation of that. For example, in phi cube theory, we have a 1-point function, and so on. All possible such diagrams. There's a 2-point function in all theories like this, tree level, and then at loop level, depending on the theories, you have different diagrams. For example, this is a phi cube diagram that I just drew here. If you have a phi 4 theory, then there's the diagram at loop level like this. And there are infinite such quantities. All of them, each one of them is represented by a sum of infinite number of such diagrams. That is basically the perturbative evolution of the QFT. And then you have Feynman rules. Feynman rules are certain prescription which tells you how to write a mathematical expression corresponding to a particular diagram. So that provides mathematical expression corresponding to such diagrams. And this is what we have done so far, quite in detail. And also we have discussed effective action and so on. But the basic message is that there are diagrams, and then there are mathematical expressions corresponding to those diagrams. But we haven't evaluated those mathematical expressions, which is our next job. So now to proceed further, we shall carefully investigate these mathematical expressions, and what we will see is that these diagrams, this mathematical expression produces divergences. So a careful investigation tells us that these math expressions have divergences. And our next effort in this course will be to understand what these divergences mean and how to tackle them, and how we could make sense out of this theory which has such divergences. And the first step will be to classify such divergences. First, see how divergences appear, and then classify this. So steps that we shall follow is how divergences appear. And then next we will do how to classify divergences. And then we will proceed further to deal with what we should do with this theory after understanding the pattern of the divergences that appear. So in this lecture and the next, this is what we this is what we aim to achieve. And so let us begin the discussion of divergences in Feynman graphs. Now consider connected Green's function in momentum space. And that takes the form, so connected Green's function, E is the number of external lines. It's a function of all the PIs. PIs are the external momenta that are coming into the diagram. And then it has a form of, for each such external line, we have a propagator delta tilde P1 and so on. And then we have the amputated part. This is the amputated graph. When you remove the external lines, I have removed the external lines, I've kept them separately. And so this is how the structure looks like. So E is the number of external lines, and this is an amputated graph. It has only internal lines, okay? And just to keep some more space, let me try to push things a little. And there are two types of such lines, these internal lines. One type of internal lines are the tree lines. We shall denote them by the momentum, the momenta carried by such tree level internal lines. We shall denote them by Q's, and they are all fixed by P's. Because of the momentum conservation, we know that at each vertex, the momenta, all the momenta that are coming into the vertex sum up to 0. And if there is any internal line within the amputated graph, which is at the tree level, then that momentum corresponding to that line gets completely fixed by the external momenta. And that we have already seen. And there is another type of internal lines, which are loop lines. It is a line which is part of a loop, and through which certain momentum that is flowing, which is not fixed by the external momenta. And those corresponding to this type of loop momenta, we will have integration. So we will denote them by L's. So L's, they are integrated over. Okay, these are the two types, Q's and L's. And so let us look at the general structure of this amputated diagram. We are considering, say, for a fixed small n, whatever I'm writing now true for fixed small n. So general structure will be, so let me write it explicitly, for V is equal to lambda n by factorial n phi to the power n. A tilde of E pi will have a form which can be expanded in the number of loops. So it has infinite number of terms, and each term has number of loops. And so you can count those terms by the number of loops, and so you can write them as summation over loops, some coefficient f corresponding to that loop L, which is a function of p lambda m, the external momenta, the coupling lambda, and mass that that the field carries, and I of L comma capital N P of M. So we have I have separates where I L comma capital N P M is the integration part of this in loop momentum integration part of this amplitude. Let me write it down and then make comments. So I L comma N P M will be given by product over J DLJ equal to 1 to L, and then product over K equals 1 to N J A K J. This is what the form of I is. So what I'm trying to say is that I will give some examples, and but let us first understand what the statement is. The statement is this is that the amputated diagram has a loop expansion, and for any particular value of the loop, there are capital L number of loop integration. So that those are LJs, J going from 1 to L, and then capital N number of internal lines. A claim is that when you fix number of external lines and number of L for a fixed value of N, that is not going to change. It is important. So if you take capital E and capital L fixed, then capital N also gets fixed. I will not argue it now. I will argue it towards the end of next lecture. But let us assume that that is true, because otherwise one would be confused about why there is an N dependence here, but there is no N dependence here. There is no summation, separate summation over N. So N looks like a, so how this equation is making sense? The reason is that N can be viewed as a function of L and capital E. So when you fix L and E, N also gets fixed. So so there are L loop integrals, and it is an integration of a bunch of propagators, and those propagators are N propagators because there are N internal lines, and they have this general structure where which will be some linear combination of L's and the external momenta Pi's. Okay, so and so some linear combination of L's and P's, and then plus m square and minus I epsilon prescription inverse. That is the propagator. Okay, so let us look at some example. Let us consider this one loop diagram. in phi cube, um, P going in L, and this is L plus P. Of course, when corresponding to this is the diagram that the way I drew it, it is not an amputated diagram. You have to ampute. Okay, so actually these are amputated diagrams, in fact. Yeah. So I have amputated this. So A will not contain, A does not contain the external lines here. A only has this part, and but that part has information about the external momentum P. And in this case, you have I 1, 2, because it is a one loop, and there are two loop lines. Okay, there are two internal lines. So that is given by integral dl, and then you write two propagators corresponding to this line and this line. So that will be L square plus m square minus I epsilon inverse times L plus P whole square plus m square minus I epsilon inverse. So you see, it's a product of n factors, in capital N factors, capital N being 2 here. There are two lines. It's a product of capital N factors, just like this. In each factor, the structure is that you have m square minus I epsilon always sitting there, but then there's a momentum part, and then momentum part is some linear combination of L's and P's, square of that. Yeah, so that is the structure here, and then there is an integral over the loop momentum. This structure is same in any theory with phi to the power 2 plus s interaction. So same structure in any theory with phi to the power 2 plus s interactions, because this one loop diagram is universally present in any. So these are two plus s vertices. Okay, but the point is that all these external momenta are getting injected at this point, and so this line will carry the sum of all these external momenta, whatever number of moment lines you have, depending on the vertex order of the vertex. So so it will be the same expression, with P being the total momenta that is coming in through the through different lines. But the structure of this one loop diagram, the mathematical expression is exactly the same. And in any theory, any polynomial, so this is like I have drawn it for phi cube for higher n's. So 2 plus s equal to s is greater than or equal to 1. So in all such theories, that means this will appear universally as a subgraph. It will sit inside the graph. It take any value of s, any phi to the power n greater than or equal to 3. You will generically have diagrams where this will sit inside, and correspondingly you will have to evaluate this mathematical expression. So this one must appear as a subgraph in any polynomial interaction, real scalar theory. let's consider the second example. This is a 5-4 theory example. This one loop diagram. This is L1, this is L2, and this is L1 plus L2 plus P. Right? And this will be, it is a 2 loop and 3 propagators, 3 internal lines. So this is a 2 loop diagram, and there are 3 internal lines. So I2 comma 3 will be given by integral dl1 dl2, and then 3 propagators, L1 square plus m square minus I epsilon inverse, L2 square plus m square minus I epsilon inverse, and right, this also has the same structure. There are 3 internal lines, and therefore there are it's a product of 3 factors whose general structure is a linear combination of momenta square plus m square minus I epsilon inverse of that. Yeah, and then what about the number of loops in the loop momenta? They are integrated over. Okay, and this contribution will be universally present in phi to the power 3 plus s theory. Now let us consider another example, which is the same diagram but repeated. So you name it L1, L2, and then L1 plus L2 plus P. Then this is an internal line. This is an internal line, you can call it Q, but Q is same as P because of the momentum conservation in this. So if P goes out, if it at each vertex you preserve momentum conservation, then P will come out. So that is an internal momentum which is at tree level, and therefore gets fixed uniquely by P, by the external momentum. And then let me call this L3, L4, and L3 plus L4 plus P. So in this case, you see in the entire diagram, there is a, so for the other 2 diagrams, this if if corresponding to this diagram, first 2 diagrams were independent of P. So this if had, of course, this for each vertex, one would have vertex factors, which is lambda square here, and they are all in P in this F. But F did not have any P dependence because it is basically a 1pi diagram. This is not a 1pi diagram. If you calculate this entire diagram, these are external legs which are amputated, and you will have, this is a 1pi part. From 1pi part you have an integral. From this 1pi part you will also have an integral, but this propagator will be there, and that propagator will depend on P, and therefore if in this case you have a non-trivial F which is going as which will go as, you know, the lambda dependence will be 1 2 3 4 4 vertices. So there will be lambda to the power 4 times it's a 5/4 theory, so lambda 4 to the power 4 times the propagator, which is p square plus m square minus I epsilon inverse. That will be f, but we will separate that out from, we have separated that out from I. For I, it is, look at that number of loops and the internal lines. So this is 1, 2, 3, 4, 4 loops, and there are 1, 2, 3, 4, 5, 6. 6 lines, 6 loop lines. So therefore, it is I. So I have I 4, 6, which should be, since it is I 4, 6, there are 4 loop momenta. So DL1 to DL4, and then there will be 6 propagators. So 6 factors of this kind of factors. There are 6 of them. So that is L1 square plus m square minus I epsilon inverse L2 square. Then we had L3 square plus m square minus I epsilon inverse. So I hope this is clear exactly how, what actually I mean by this I integrals, where I've separated the essential integration part of an amputated amplitude. And so now, and also we understand that this additional factor, the p dependence in that will come if the diagram is non-1pi. If it's a if it's a 1pi diagram, then it will only contain, a bunch of numerical factors and the powers of lambda. There will be no p dependence, but p and m dependence will come when it is non-1pi, because there will be internal lines which are tree level.